Welcome to our video series. Today we're discussing distillation for operations personnel, part 1. Tell you a little bit about KLM Technology Group, based in the USA since 1995. KLM is a technical consultancy group providing specialized services and equipment to improve process plant operational efficiency, profitability, and safety. KLM's core business is we do training. We do in-house training, we do regional conferences, and we do videos, such as what we're doing today. Engineering design guidelines, we'll talk more about that. We do process engineering, optimization studies, energy studies. We do hazard facilitation, facility siting studies. We do basic engineering with our key partners. We do detailed design packages. We sell process equipment, random packing, structured packing. We have a great engineering magazine called Engineering Practice. We do unit commissioning. We do distillation equipment inspection. All right, so it's very important for you to install the equipment correctly. We do unit benchmarking, and we do evaluation of process units. Today we're discussing distillation for operations personnel. We also offer distillation design, operation, process control, and troubleshooting. For engineering and operations, we do advanced process simulation training. We do distillation for operations, which is what we're doing today. Distillation commissioning, distillation process control, as well as other process unit and equipment groups. We do a whole group on ethylene. We do a large group on refining. We do a large group on natural gas processing. They can be found on our website, klmtechgroup.com/training. We have the Coleman's Handbook of Process Equipment Design. In the Coleman's Handbook, we have multiple chapters on distillation. We have distillation column sizing, 147 pages. Distillation tray hydraulics, which we'll talk about in part 2. We have 50 pages. Packing, reboiler design, process control, refinery crude towers, refinery ethylene towers, ethylene quench towers, BTX design, and 3 chapters on natural gas processing. There are multiple chapters on distillation in the Coleman's Handbook. There are multiple chapters. We have over 140 individual chapters on a wide range of subjects: pumps, compressors, control valve, relief valves. Each chapter is 80 to 120 pages, including design and sizing guidelines. As we revise the chapters, we're adding troubleshooting sections. The handbook can be found here, klmtechgroup.com/engineering design guidelines home. Today we're discussing distillation for operations personnel. Part 1, which we're going to talk today, is introduction, types of distillation, types of stages. Part 2, types of trays, types of packing, and overview of hydraulics. I think it's important for operations personnel to understand hydraulics. They need to understand flooding. They need to understand weeping. They also need to understand the internal flows inside of a distillation column. I go a lot of places because they don't understand tower hydraulics. They don't do the right process control. And so it's important for operations personnel to understand how trays are designed, and then you can understand how to do proper process control. Distillation is a separation of key components by the difference in the relative volatility or boiling points. So if their boiling points are close together, it's difficult to do by separation, by distillation. It can also be called fractionational distillation or fractionation. For close boiling mixtures, many stages are required to reach the desired purity. So distillation is favored over other separation techniques such as crystallization or membranes when the boiling points are far apart. When products are thermally stable, larger rates are desired, no corrosion, precipitation, or explosion issues are present. Distillation is the most common separation technique, and it's energy intensive. In a refinery, distillation can consume more than 50% of the plant's operations energy cost. So the highest cost is typically the feed. The second highest cost is the energy. If you understand distillation and how distillation is designed and how it should be controlled, you can save a significant amount of energy. Okay? The correct equipment selection can reduce both, can improve your feedstock utilization, it can improve your recovery, and it can reduce your energy. All right? And so it's important that you not just buy vanilla equipment. You need to buy equipment that has energy improvements and has purity improvements. In KLM, and it's really roughly the same cost. A bad distillation tray and a good distillation tray almost cost the same amount. It's just how they're designed. One way to improve an existing plant's operating cost is to improve their efficiency and operations by process optimization and control. So we can take an existing plant, we typically can go in and do a high-load test, and we can improve the efficiency and the purity of most of the products. But you can't really do that until you first understand distillation principles and design. So we're going to try to, next two videos, we're going to talk about how to get better energy, how to get better efficiency. There's two types of distillation columns in general. There's batch distillation, and then there's continuous distillation. And in continuous distillation, there's different types. Can be a single feed, can be multiple feeding products. You've also got what's called extractive distillation, where you add a solvent, and you also can have reactive distillation, where you add some catalyst in the column. Batch distillation, there are many types of distillation. Each are designed to perform specific types of separations, and each with different characteristics. They have two main classes. These are batch distillation and continuous distillation. Batch distillation, the feed to the column is introduced in a batch wise. So the column is charged with a batch, and then the distillation is carried out. When the desired task is achieved, the next batch of feed is introduced. So typically batch distillation is for like high value products in pharmaceuticals, and you'll put a batch in there and try to recover all the expensive pharmaceuticals that you can. In contrast, continuous distillation processes a continuous feed stream. No interruptions normally should occur unless there's a problem with the column or the surrounding process units. They're capable of handling high throughputs, and they're the more common of the two types. So you got batch distillation, which is typically for high value products. They're used a lot in pharmaceuticals. And you've got continuous distillation, which is used mostly in refineries and ethylene plants. And if you have high throughputs, you're probably using continuous distillation. So here's a picture of a continuous distillation column. I put the feed in. Above the feed is called the rectifying section. Below the feed is called the stripping section. So I'll go overhead to the overhead condenser. The vapors are cooled. I go to the overhead receiver. And I put some back to the column as reflux. I make an overhead product. I go through the stripping section at the bottom. I go through the reboiler. And then I go out the bottom's product. Variations may be utilized in continuous distillation column. The column may have multiple feed points and multiple products, like a crude column. It has one feed, but I have multiple products. So there can be multiple, and some columns can have multiple feeds and multiple products. The column may have a solvent added to the system to increase the separation. This type of column is called extractive distillation column. The column may have a catalyst bed and a small reaction occurring in the column. This type of column is named reactive distillation column. This is a picture of a extractive distillation column. We have an article that we wrote about this particular set of columns and trays. So the solvent's added in the middle of the column. The solvent comes down the column. The feed is added kind of in the bottom, and then then the bottom of the column then goes to the feed of the stripper. So this is called the extractive distillation column. This is a reactive distillation column where the tower feed comes in, you add some hydrogen, you may go through a catalyst zone, and you come up the overhead condenser, you go to overhead receiver, you remove the hydrogen, and then you make a net overhead. All right, and then you have the bottoms. So this is a reactive distillation column. So I've got types of columns, and we got types of stages. All right, so there's multiple types of stages. In part 2, we'll talk about different types of trays. So we'll talk about dual flow tray, bubble cap tray, sieve deck, valve, and then we'll talk about random and structured and packing. So that's in part 2. All right. So flash drum. The simplest type of distillation device is a flash drum. It's a single stage and can reach 100% of equilibrium limits if there's sufficient time. Typically, you need about 5 minutes to reach equilibrium, and we call equilibrium 100% efficiency. All right. Simple flash. An overhead receiver is an example of a flash drum. A 50-50 mixture of ethylene and propylene can only be separated to about 80-20 in a single flash drum. Okay. Typically looks like this. Pretty straightforward. I come in, got overhead vapor, I've got overhead liquid. It's important for operations people to know that a overhead receiver typically is designed for 5 to 10 minutes of residence time. All right, so you need to understand that none of these vessels you can put feed in for very long without pulling feed out. There was a major incident at Texas City where they put feed into a column for multiple hours. And I don't think anybody there understood that an overhead receiver is designed for about 5 to 10 minutes residence time, and a reboiler in the bottom of the tower is designed for about 5 to 10 minutes residence time. So it's an operations person needs to understand these vessels are not designed to hold hours and hours of fluid. They're designed to hold about 5 to 10 minutes of feed. Reboiler condenser. A reboiler is a flash drum with heat exchange. It can approach 100% of equilibrium limits if there's sufficient residence time. The 3 normal types of reboilers are horizontal thermosiphon, vertical thermosiphon, and kettle drums. The best design is for the liquid from the bottom tray to pass through the reboiler at least once before being drawn off as the tower bottoms. Okay, so typical reboiler can reach 100% equilibrium. Again, it's not designed for hours and hours of feed. It's designed for 5 to 10 minutes of feed. So the bottom tray liquid comes in, it goes in the reboiler, you come out the bottom, and then this is a vertical thermosiphon. Looks like this. Reboiler condensers. A condenser is a flash drum with heat exchange. There are 3 major types of condensers. All right. There's total, there's partial, and there's a hot vapor bypass. Each has its best application. So let's look at what these 3 types of overhead condensers look like. A partial condenser is best when there's a large difference in the overhead vapor compositions. For example, when there's a small amount of methane and hydrogen mixed in a propylene stream, like in a propylene tower in an ethylene plant. The partial condenser condenses the propylene and leaves the methane and hydrogen as a vapor to be vented from the overhead receiver. This condenser works well for most applications. The system needs to be reviewed to address the potential buildup of non-condensable gases in the heat exchanger that can reduce the cooling potential of the cooler. What does it look like? Looks like this. I come off the top of the tower. I come through the overhead condenser. I come into the overhead receiver. I make the condensate liquid, which in this example might be propylene. The vapor product is hydrogen and methane. So it's very important. You see the vent on top of the overhead condenser. That vent is called a non-condensables vent. In many plants I go to, that vent is blocked in. So what can happen if the light vapor stacks up in the top of this condenser? I've taken area away from the cooling. And so what we want to do is we want to crack that vent, non-condensable vent open. I don't want to waste a lot of product, but I want to crack it open till the line is just warm. And then what you'll notice is the temperature in the reflux will come down because I've got full area now to cool the reflux. As the reflux comes down, the tower starts to work better. I've got better equipment uses. So whenever I walk up to a system, I want to make sure this non-condensable vent is open. Very important for an operations personnel to understand what this non-condensable vent is for. I don't want to crack it wide open because I'm losing product, but I do want to crack it open till it's just warm. Total condenser is best used when there's a small difference in overhead vapor compositions. The overhead vapors can be condensed at approximately the same temperature. This system also needs to be reviewed to arrest the potential non-condensable gases in the heat exchanger that can reduce the cooling potential of the overhead condenser. So it's even more important that this vent be cracked open in a total condenser because the light ends really don't have a way to leave. Okay, so you need to crack that non-condensable vent open. Crack it open till it's warm. Now I've seen on a total condenser, I've seen a significant improvement in the column operation when you crack that non-condensable vent open. So it's very important that if I'm going to do a high load test, this is one of the things I'm going to look for. Is this vent cracked open? Hot vapor bypass. The hot vapor bypass condenser is best utilized when there's potential for large changes of overhead vapor composition. The vapor bypass can be used to maintain the pressure in the tower system when the light components are lower than design. The hot vapor bypass condenser also has a lower install cost due to the heat exchanger being installed on the ground. The negatives of the hot vapor bypass is that the bypass can be opened too much, increasing the temperature of the reflux. This reduces the tray efficiency in the top of the column, raises the tower pressure, which also makes the hydrocarbons harder to separate. All right, so if the operations group opens this hot vapor bypass too much, I can significantly reduce the efficiency and the purity of the column. So I want to open that hot vapor bypass just enough to control the pressure. I don't want to open it too much. This system, because of the physical location of the heat exchanger, even has the higher potential to build up non-conventional gases in the heat exchanger that can reduce the cooling potential. So a hot vapor bypass, so it comes off the tower. I've got the hot vapor bypass control valve, which is typically manually operated, so the operator can adjust it. I come down to the overhead condenser, which is on the ground. And it's even more important that I crack open this non-condensable vent for this system. Then the cooling goes back up to the overhead receiver, goes in and leaves. Okay, these are typically designed for C4 columns, debutanizers. So I see a lot of this hot vapor bypass on a debutanizer type column. It's very important for operations to understand. I don't want to crack this. I want to minimize the use of the hot vapor bypass because I want to push as much as possible through that condenser so the reflux will be cooler. Reflux is cooler, I get better stage efficiency, and I get better purity on my products. So it's important that operations groups understand the principles and how best to operate hot vapor bypass systems. Distillation. One of the major unit operations and processing units, energy intensive, but it has the opportunities to be optimized. Product recovery and impurities can be improved by understanding the principles of distillation. These principles need to be understood in advance of operating and troubleshooting a distillation column by the operator or problem solver to be effective. Thanks for your time. This is part 1. We'll also have a second video which goes into more details in part 2. Thanks for your time today.